Right now, somewhere on this planet, a kiln the length of 2 football fields is spinning in the dark, glowing orange from the inside, reaching temperatures hotter than flowing lava. Inside that kiln, ordinary crushed rock is undergoing a transformation so violent and precise that if the temperature drifts by even 50 degrees, the entire batch is ruined. And the product of that inferno? A gray powder so plain-looking, you could mistake it for dust. Yet that powder is the single most consumed manufactured material on Earth. Humanity produces over 4 billion tons of it every single year. More than food, more than steel, more than plastic. It holds up your apartment building, carries your car across a bridge, and lines the tunnel your subway passes through every morning. But here is what almost nobody ever stops to consider. The chemistry inside that kiln is so complex, so dependent on crystal structures forming at exact temperatures, that scientists are still publishing papers trying to fully understand it. This is the story of how we turn mountains of limestone into the invisible glue holding civilization together. This is how cement is actually made. Before a single rock enters a kiln, the process begins with geology. Cement manufacturers do not simply dig up any limestone and throw it into a furnace. They need limestone with a calcium carbonate concentration hovering between 75 and 80%. Too low, and the calcium content will not produce the right compounds during firing. Too high in magnesium or sulfur impurities, and the finished cement will crack, expand, or lose strength within months of being poured. Finding the right deposit is more like prospecting for a pharmaceutical ingredient than mining gravel. Geologists drill core samples across potential quarry sites, running chemical analyses on every layer to map out exactly which seams are usable and which need to be avoided or blended away. Once a suitable deposit is identified, the raw material preparation begins, and this step is far more involved than people realize. Limestone gets blasted out of quarry walls and fed through a cascade of crushers, jaw crushers first to break boulders down, then impact and hammer mills to pulverize the stone into fragments smaller than a walnut. But limestone alone is only part of the equation. Clay provides the silica, alumina, and iron oxide that must react with the limestone's calcium during firing. Manufacturers blend these materials in ratios hovering around 80% limestone to 20% clay, though the exact proportions shift constantly depending on what the chemical analysis reveals about that day's raw material. This blended mixture, called raw meal, needs to be extraordinarily uniform. Even slight chemical inconsistencies can produce weak spots in the final cement. Modern plants rely on automated X-ray fluorescence analyzers that scan the raw meal composition in real time, making continuous micro-adjustments to the blend before it ever reaches the kiln. Now comes the question that separates modern cement plants from one another. How do you prepare this raw meal for the furnace? There are 2 approaches. The dry process dries and grinds the raw materials into a fine powder before feeding it forward. The wet process mixes everything into a slurry containing 30 to 40% water. On paper, the wet process sounds wasteful, and in terms of energy, it absolutely is, because you are paying to evaporate all that water before any useful chemistry even begins. But the wet process allows for easier blending when dealing with sticky, high-moisture clays that resist uniform mixing in a dry state. Most modern facilities have migrated to the dry process because the energy savings are enormous, but a handful of older plants still run wet kilns, particularly in regions where the local raw materials practically demand it. Here is where things get truly dramatic. The rotary kiln is the beating heart of every cement plant, and it is an engineering marvel that most people have never seen. Picture a steel cylinder stretching over 200 meters long and 6 meters in diameter, tilted at a slight angle, rotating slowly day and night. Raw meal enters the high end, and gravity, combined with the slow rotation, carries it gradually downward toward a flame burning at nearly 2,000 degrees Celsius at its core. That flame temperature matters enormously. Kiln operators monitor it obsessively, sometimes adjusting the burner position or airflow multiple times per shift, because the flame shape and intensity directly control the chemical reactions happening inside the material bed. As the raw meal descends through the kiln, it passes through distinct reaction zones, each one transforming the material further. In the first zone, between 200 and 800 degrees, residual moisture evaporates and organic matter burns away. Between 800 and 1200 degrees, something critical happens. Calcium carbonate decomposes in a reaction called calcination, releasing carbon dioxide and leaving behind reactive calcium oxide. This is one of the two major sources of CO2 emissions in cement production, and it is inherent to the chemistry itself. You cannot make cement from limestone without liberating carbon dioxide. It is baked into the physics of the raw material. Beyond 1200 degrees, things get genuinely exotic. The calcium oxide begins reacting with the silica, alumina, and iron from the clay to form intermediate compounds. A partial melt develops, creating a liquid phase that acts as a medium for the final, defining reaction. At around 1450 degrees, the calcium silicate combines with additional free calcium oxide to form tricalcium silicate. In cement chemistry, these two compounds are known by the names a Swedish researcher gave them in 1897, belite and alite. Understanding the difference between these two minerals is the key to understanding why cement behaves the way it does, and this is where most explanations of cement production stop short. Alite, the tricalcium silicate, is the dominant mineral in finished cement and the primary source of early strength. When you pour a concrete foundation and it becomes load-bearing within days, that is alite doing the work. Its crystal structure contains oxygen vacancies, essentially missing atoms in the lattice, that make it highly reactive when exposed to water. Belite, the decalcium silicate, reacts far more slowly. It contributes almost nothing to early strength but continues hardening for months and even years, providing the long-term durability that allows concrete structures to stand for decades. The ratio between alite and belite in a batch of clinker determines whether the cement is suited for a highway bridge that needs to carry traffic within a week or a massive dam that must cure slowly to avoid cracking from internal heat buildup. What makes this even more fascinating is that both alite and belite exist in multiple crystal forms called polymorphs. Alite can crystallize as monoclinic or triclinic variants, and the monoclinic form is far more reactive, meaning it produces stronger cement faster. Belite has at least 5 known polymorphs, ranging from the highly reactive alpha form down to the gamma form, which is essentially inert and useless for construction. The polymorph you end up with depends heavily on what trace impurities are present in the raw materials, and critically, on how fast the clinker cools after leaving the kiln. This is why cooling is not just a logistical step, but a make-or-break chemical decision. When clinker exits the kiln at roughly 1400 degrees, it must be cooled rapidly to lock in the desired crystal structures. If it cools too slowly, alite begins reverting back into belite and free calcium oxide, essentially undoing the most energy-intensive reaction in the entire process. Modern plants use massive grate coolers that blast ambient air through the hot clinker, dropping its temperature to around 100 degrees within 20 to 30 minutes. This rapid quench preserves the metastable alite crystals and prevents belite from transforming into its useless gamma polymorph. The hot air recovered from this cooling step gets redirected back into the kiln as preheated combustion air, creating an elegant energy loop. The cooled clinker, now a collection of dark marble-sized nodules, enters the final stage: grinding. Ball mills loaded with heavy steel spheres pulverize the clinker through sheer impact and friction. During this stage, roughly 3 to 5% gypsum is added, and its role is deceptively important. Without gypsum, the aluminate phases in the clinker would react with water almost instantaneously, causing the cement to flash set into an unworkable mass within minutes of being mixed. Gypsum slows this reaction just enough to give workers the window they need to place, shape, and finish the concrete before it begins hardening. Once ground to the desired fineness, the cement undergoes rigorous quality testing. Laboratory technicians cast standardized mortar cubes and crush them after 3, 7, and 28 days to verify compressive strength. They test setting time, volume stability, and heat of hydration. Only after clearing every benchmark does the batch receive approval for sale. But here is a detail that connects all of this back to a question scientists are still chasing. 2,000 years ago, Roman engineers built harbor walls and breakwaters from a concrete made with volcanic ash, quicklime, and seawater. Many of those structures are still standing. In 2023, researchers from MIT and Harvard discovered why. The Romans used a technique now called hot mixing, incorporating chunks of reactive quicklime directly into their concrete. When cracks formed and water seeped in, it reacted with those lime clasts to produce new calcium carbonate crystals that sealed the fractures from within. In marine environments, seawater percolating through the concrete triggered the formation of a rare mineral called aluminous tobermorite, which grows in interlocking plates that actually reinforce the material over time. The ocean was not destroying Roman concrete. It was making it stronger. Modern Portland cement has no equivalent self-healing mechanism, and researchers are now actively working to engineer one inspired by this ancient chemistry. The environmental stakes could not be higher. Cement production accounts for roughly 8% of global carbon dioxide emissions, split between the fossil fuels burned to heat the kilns and the CO2 released chemically during limestone calcination. The industry is pursuing multiple strategies simultaneously: substituting waste-derived fuels for coal, replacing a portion of clinker with supplementary materials like fly ash and blast furnace slag, developing belite-rich cements that require lower kiln temperatures, and experimenting with carbon capture systems bolted onto existing plants. Some researchers are even exploring entirely new binder chemistries that bypass limestone altogether, though none have yet matched Portland cement's combination of performance, cost, and scalability. Every bag of cement sitting on a hardware store shelf represents an extraordinary chain of events. Millions of years of geological compression created the limestone. Geologists mapped and tested the deposit. Engineers blasted, crushed, and blended the raw materials to precise chemical specifications. A kiln hotter than a volcano transformed that blend through a sequence of reactions that depend on crystal polymorphism, liquid phase sintering, and rapid quenching. And a Swedish scientist naming tiny crystals under a microscope in 1897 gave us the vocabulary we still use to describe what happens inside that inferno. The next time you see a concrete wall, a sidewalk, or the pillars of an overpass, remember that you are looking at chemistry performed at the edge of what rock can withstand, frozen in place, and asked to hold up the world.